In week 6, we're going to introduce our final set of operators that we can use with our variables, and introduce this logical data type. And then we'll jump into branching. So we already talked about data types a little bit in week 5, where we have numerical values stored as doubles. We also introduced this idea of a string, scalar, which is double quote string, versus a character array, which is single quote string. But we also have logicals. So logicals is another data type where it can store one of two values, true or false, and represents the answer posed by what's known as a conditional expression. So any non-zero number is considered true, so just keep that in mind. Typically we use the number 1. We can also type the word true. You can see it in MATLAB, it shows up as blue, it's a keyword. And then false is represented by the number 0, and 0 is the only numerical value for false, or we could type the word false. And we get logical variables when we use relational equality and logical operators, or when we type the words true or false. So relational equality and logical operators are used to form these conditional expressions. You're probably familiar with equality and relational operators. These are the ones that you're probably used to. These are the only ones. Relational and equality operators are used for comparison, where we can compare less than or equal to, greater than or equal to. This is our MATLAB syntax. So note, if I want to do less than or equal to, I do less than sign followed by equals with no spaces. If I want to do greater than, it's greater than equal sign, and then equal with no spaces. If I want to check if two things are equal to each other, then I use the double equal sign, so no spaces. And if they're not equal to each other, then I use the tilde, which is shift the key next to your 1 on your keyboard, and that's not equal to. So do keep in mind, equality is not the same as assignment. Equality is comparison. This is a common error with 2 equal sign. Assignment is storing values in a variable. Okay, so double equal sign is not the same as single equal sign. Don't confuse the two. And then one other thing to note, when we're comparing for equality, we shouldn't compare floating point numbers. Floating point numbers are numbers with digits past a decimal point. Instead, we should compare them for equality, quote unquote, and call it equality, by using absolute value of num1 minus num_b and check to see if it's greater than or it's less than a tolerance. And the reason for that is round off error. Our computers do not have infinite precision. They do stop at some point in time. They cannot store values to infinity, so there's some round off error. So depending on how the value is calculated, two numbers that look the same might not actually be exactly the same. So just keep that in mind. But if we have integers, if we have string scalars, equality is great to use. Most students are familiar with those. New thing for most students is a logical operator. So logical operators are used to compare two logical values. So it's used to compare true and true, or false and true, or false and false. And this results in another logical value. So there's 3 different logical operators. We're not really going to use XOR, but you'll see how it works. And we've got logical and, logical or, and logical not. And here is called a bar. On your keyboard, it's shift / it's right above enter, but it's bar. That's what you'll hear me call it. But and is ampersand. That one students usually know. But and, there's 2 ands and 2 ors. They're literally the same. However, these ones should be used with arrays, and the double ampersand and the double bar should be used with scalars. So I'll let you guys know, arrays will be used with logical operator or logical indexing, scalars will be used with branching statements, and we'll talk about those. The double ampersand and double bar is called short circuit operator. Its code can be executed faster. And then logical not, that's the tilde still. And we saw that with the not equals to, that's the tilde. Those are more challenging to students, so let's look and see how they work. So here's what's called a truth table. Essentially identifies how and or and XOR and not function. So here are my 2 inputs, or we'll call them operands, is the mathematical term, where here my first operand, which would be I1, and then here's my operator, and I2. I1, it's either true or false. And I true is true or false. And here's how it results if I have and here as my operator. And you'll notice and gives me a true only when both of these are true. Okay, otherwise it's false. So it's checking to see, is I1 and I2 true? That's the and. They both need to be true. So that's how true, or that's how and works. They're both true. For or, you'll notice or is true as long as one of them is true. So if I have or in here, it's saying, okay, is I1 or I2 true? That's what question is asking. So note it's only false if both of them are false. If one of them is true, or is true. For XOR, like I said, we're not really going to use it, but you'll notice it's true if they're different. So if one is true and one is false, otherwise it's false. And then not. Not only works with one operand, so it would be not I1. So you'll notice if I1 is true, then not true is false. And that makes sense. It's inverse. It inverts it. Makes it true to false and false to true. Okay. So we have those operands. We have relational, where we've got less than or equal to, less than or equal to, greater than, greater or equal to. We've got equality and not equal to, and we have and, or, and not. We can use these operators to compare pretty much anything as long as we understand how they work. So we can compare scalars and arrays. If I compare two scalars, then a scalar logical is produced. Logical meaning true or false. So you'll see MATLAB printed out as a logical 1 for true and a logical 0 for false. If I compare two arrays, then it's going to compare element by element to produce another array of logical values. Element by element, notice they need to be the same size. Just like it was for element by element operations. Element by element math. Okay, we can also compare a scalar to an array, and we actually do this a lot, where it just compares the scalar to every single value in the array. Okay. For strings, for text, there are some caveats to this, so we need to understand how these apply to text. For string scalars, we can use the same operators that we used for math. We typically don't check to see if it's less than or equal to. It will alphabetize them if that's what you do. But we can use the equality operators, so we'll see this often. We'll see string 1 equal to string 2. Note it is case sensitive. If you want it to be case insensitive, you just convert it to all lowercase. Or all uppercase. To all lowercase. Or there's probably an upper function, but that's what the lower function does. Converts the whole string to lowercase. The difference between string scalars and character arrays is strings, this is a 1 by 1. So it's comparing the whole string to the whole string. For a character array, though, it's not a 1 by 1. So this string here, if I use single quotes, would be a 1 by 7 because it has 7 characters in it. So if I tried to use equality, oh, I have it written down. If I try to use equality, it's going to perform element by element because that's how it works with numerical arrays. It's going to check this, if this is equal, if that's equal, and it'll give you a true or false for every single value. So my answer would be true, 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 0, false. If we want to compare the whole single quote string, we can use the string compare function, where that essentially does a check for this is the equivalent of this, where it checks to see, okay, is this whole string equal to this whole string? It compares the whole thing. If we want to do insensitive, we can use string compare I for insensitive. Okay, I recommend you use double quote strings for comparison because it matches your logical comparison that you use for numbers. So use double quotes. They're super powerful. When you're using fprintf and disp, I don't care if you use double quotes or single quotes. But for most things, double quote strings are really useful. Okay? And this is one of the reasons why. Okay, so we've got relational, equality, and logical operators. These can show up in mathematical expressions. So we need to make sure we understand the order of precedence. And this is our full order of precedence given all of the operators in this class. So first is parentheses. It's always parentheses. It's always the case. And then we have exponents. Follows our logic so far. Then we have not. So not is evaluated third. So just as a note, keep that in mind. And then here we have more math. Multiplication and division are equal precedence working left to right. Addition and subtraction, equal precedence working from left to right. Follows normal math. And then we have relational, so these ones are our new ones. And then we have equality, so note, relational is not the same precedence as equality. Once we have those, then we have logical and or, and these are the single quote, or the single ampersand and the single bar. So use these with arrays. And then we have short circuit and, so the double and the double or, these are used with scalars. And then we have assignment, which is performed last. Okay, so that's our full order of precedence. So exponents, or not exponents, parentheses, carets, not, multiplication, division. So asterisk, divide, addition, subtraction, relational, equality, logical and, logical or, short circuit ones, and assignment. Okay, not always terribly important, but you really should understand order of precedence. Most of the time, we're going to be using these operators, relational, equality, and logical operators, in branching statements. But MATLAB also gives us some unique functionality to use them in what's called logical indexing. So if you remember, indexing is the word that we use to access individual elements inside of a vector or a matrix. And we have two sides to this equal sign, where on the left-hand side we have a variable. And we're asking, what do we want to store in that variable? Store things here. Or modify. I should say modify as well. And we introduce these additional questions where we can say, okay, do I want to modify the whole variable? Do I want to modify part of the variable? Which part? Which rows? Which columns? And then we said, what do we want to put there? So some other data. What to put there? And that data, it could come from a whole variable. It could come from part of a variable. Which part? Rows, columns. So we've got this indexing that we can use in order to access and modify and insert values from a whole array, from part of an array, part of the rows, part of columns, and that's really powerful. Logical indexing takes it one step farther, where now instead of being location-based, we can also make it value-based, where here I have the left-hand side and the right-hand side, where I can say an array of logical numbers. So, for example, if this logical array is created by saying array greater than 0, so all my positive numbers. So this logical array, here I have an array greater than 0, so it's going to be true wherever the values in this array are greater than 0, and false wherever they are not. That's what this logical array stores, the true and false values for this expression. When we do that, when we say array, logical array, this logical array needs to be the same size and same orientation as that array, which makes sense, where all of the values in my array here that correspond to true in my logical array are going to be extracted out and placed in this array as a single column. So that's important, it's a single column. Previously, we had location-based, and it created the same orientation, but that's not guaranteed anymore. So it's going to take all the locations where this is true, for this array, everywhere this is true, it's going to take them out, store them in this array. Everywhere it's false, it's going to ignore them. This is logical indexing, and it's super, super useful in MATLAB. It's not very much in terms of our notes, but it's really important you understand this because it shows up on the midterm. It's really useful, it's very helpful. So we will go over several examples in class, but make sure you understand this concept. Okay, in order to understand this concept, you need to understand indexing, where we're saying A, which part of A, which rows, which columns. Where now we're expanding it to say A, which part of A, the part where A is greater than 0. Okay, so that's logical indexing. It's very unique to MATLAB. Very unique to MATLAB. You can do this in other languages, but usually it's more than one line of code. Whereas in MATLAB, it's one line of code. Okay, the last topic for this week is branching. And this is definitely a topic that you do in every other programming language, branching, because it allows us to make decisions. Which a computer program is just a series of code, but a computer makes decisions all the time. This is how it's making decisions, with branching statements. So it's a group of code that allows us to decide whether or not to execute one group of code over another or other groups of code. And these are based on questions that we ask using the relational equality and logical operators. And these questions are called conditional expressions. So these are our questions. Okay, using relational equality and logical operators. The one thing to note is when we use branching statements, we need a scalar, single, true, false answer. Okay, so that can be confusing, but we do need a single answer for branching statements. Where it follows this, here I have my code, and then I hit a branching statement where I'm making a decision. So I'm going to say, okay, is A greater than 0? Is it a positive number? If that is true, I'm going to do this. If that's false, I'm going to do this instead. So I'm choosing between branch 1 and branch 2. If it's true, this is ignored. If it's false, though, this is ignored. So I can't have both branches executed in the same set of code, because A is either true, or A greater than 0 is either true or false. The most general branching statement that we're going to use is an if statement. It can be used in all branching situations. It's our default, and if you only remember one branching statement, remember the if statement. Where the if statement will allow us to choose between one of many groups of code. And the block of code that's going to be executed is the one corresponding to the first true conditional. So the first true conditional. And that's important to understand, because if we understand how an if statement works, then we can write efficient if statements. We can minimize the amount of code we have to write, the number of comparisons we have to write. So it's going to be the one corresponding to the first true conditional statement. We're going to have lots of branching statements, lots of things grouped together. So it's important that our code is organized. MATLAB will automatically do this for you, and it will do something called indenting, where code blocks are indented by 3 or 4 spaces, depending on what you define as a tab, to easily identify the code that is associated with the corresponding conditional. If you want to automatically indent things in MATLAB, you can say Control I. There's also an automatic indent button on the ribbon at the top. But indentation is super important when we get to branching statements, because it helps us see how our code is organized. So if statements. Here you can see that indenting. So our most basic if statement looks like this. If conditional expression, this here is our question. So if A is greater than 0. If that is true, I'm going to execute the code inside. And you can see it's indented to indicate that, hey, this code is associated with this conditional statement. So I'm going to execute the code inside if A is greater than 0. But if that's false, then I ignore this, and this code is never even executed. It's never touched. Okay, so that's our most basic if statement. Every if statement needs to start with the word if and end with the word end. So every function has an end, every if has an end. So you can see this code might not be executed, which is fine. That's what we want. We only want to execute it if A is greater than 0. If we want to make our if statements a little bit more complicated, we can add what's called an else, where we can have a conditional expression. So if A is greater than 0, if A is greater than 0, I will execute this code inside and then ignore. Because remember, an if statement starts with the word if, ends with the word end, and it's going to choose between one of many code blocks. So it's choosing between one of these two, never both, only ever one. So if A is greater than 0, if it's positive, I'm going to choose this one. However, If A is not greater than 0, if A is less than or equal to 0, I'm going to choose this one. I don't need to ask this second question. I don't need to ask this piece here, because if A is not greater, like if this is false, then my only other option is that it's less than or equal to 0. There's no other option. So an else is my default. It's saying, hey, if this isn't true, then at least do this. Okay. So sometimes we want to write a conditional expression, but the else does not need one. So it's our implied that A would be less than or equal to 0. Okay, because I'm asking if A is greater than 0. If that's false, that's the only other option. Okay, so no else does not have a conditional next to it. And if I have more than 2 options, then I can have else ifs. So here's option 1, option 2, option 3, option 4. So I'm now choosing between one of these 4 options, where if, let's say A is greater than 10. If A is greater than 10, I'm going to execute this, and all of these are ignored. If A is not greater than 10, I'm going to ignore this one, and I'm going to jump to my next conditional. Next to this else if, I can ask another question. I can say, okay, if A is not greater than 10, that means it's less than or equal to 10. Let me check to see, okay, is A now greater than 0? If that's true, it's going to execute this, and then ignore those ones. If that's not true, then it's going to jump to my next question with this else if. So it's not greater than 10. It's not greater than 0. Let's check to see, okay, is A greater than or equal or greater than negative 10? If that's true, it'll execute this and ignore this one. If that's false, though, then it will ignore this, and it'll jump to my else. My else is my optional. If these are my conditionals, A greater than 10, A greater than 0, A greater than negative 10, then my else would be A, by default, less than or equal to negative 10. This is my default. This is my implied conditional. So note else does not have a conditional. It's my default. So if I want to expand between many options, I can have else ifs. So note, I don't need an else. I can have just an if, I can have just an end. I can have an if, an else if, and an end. I can have an if, an else if, an else, and an end. The only requirement is that we always start with an if, and we always end with an end. Else's come last. So if I have an else, it will be right before my end. I can have as many else ifs as I want, and my else is optional. Note, the else does not have a conditional. There is no conditional. I see a lot of times with students, and I've done that myself as well. Okay, but that's the structure of an if statement. It's used with any type of branching. And these conditional expressions can be pretty complicated. So they'll use relational operators, equality operators, logical operators. There's lots of things that go into writing a well-defined, a well-constructed conditional expression. So if we have branching statements, then we start to get a little bit more complicated in our code, which means we can start to write code that's unnecessary if we don't understand how it works. So if statements should be designed or written to minimize logic tests and remove redundancies. So these are some things that I recommend. Steps, there we go, steps in order to write a efficient if statement. So determine how many mutually exclusive paths are needed. How many options do we have? What are we choosing between? How many options are we going to choose? How many blocks do we need? Isolated pieces of code. Then we determine how to choose those options. What are questions we need to ask in order to choose an option? Order those from most restrictive to least restrictive. Sometimes they are restrictive, sometimes they are completely mutual. Like there's no overlap at all. So if we can identify the most restrictive to the least restrictive, then we know which order to write our conditional statements in, to write our if statement, and we can write our statement. Okay. However, if we don't know the restrictive order, if there is one, then we can write them out of order and we're not going to get the code that we want. Also, sometimes we want to write one if statement, sometimes we want to write multiple if statements, so it's important you understand what decisions you're making in your code and how to make those decisions. The second kind of branching statement is a switch statement. It's an alternative branching statement. and can only be used under specific conditions where we are testing for equality. So we're using that double equal sign or the inverse not equals to. And a switch statement looks like this. Here's our code, where it's comparing a single variable, so here's my variable for comparison, to each listed case. And each case is written out as case, followed by, if it's one option, one case, then we just write down the option. Otherwise, we can compare it to multiple with a bracket. But what the switch statement is going to do is it's going to check for equality, the variable with each case option I have listed. So is variable equal to case 1? Is variable equal to case 2? Is variable equal to case 3? Is variable equal to case 4? Is variable equal to case n? Whichever one results in it true, it's going to execute the code inside of it. So this code will be executed if variable equals case n. So note, this should only be used for equality, which if you remember, equality should only be used with integers, characters, string scalars. The only difference is it can be used for character arrays. So a lot of times when we're comparing text, we use a switch statement. And in general, it is best practice to use a switch statement over an if statement when possible to result in clear to read and understandable code. So you can use an if statement with all situations, but sometimes it is clearer to use a switch statement. One of those cases being when we're comparing text. When you're comparing text, a switch is a very natural option to use. Last thing to note, I know the video went long, but any valid code can go inside of a code block, including another branching statement. This is known as a nested structure, and this is where indentation matters significantly. So notice this code here is indented, which means all of this is associated with this conditional expression. So if this conditional expression is true, this is executed and this is ignored. However, if this conditional expression is false, then this is ignored and this is executed. And we also have another branching statement in here where we can see this double indented code is associated with this conditional expression. So if this one is true, it will execute the code inside here. If it's false, though, it will be ignored. So like I said, MATLAB will automatically indent things for you. So I encourage you, Control plus I. If you are on a Mac, it would be Command plus I. Or there's an auto indent button on the ribbon at the top. Okay. So designing if statements, there is an art form to it, understanding what decisions need to be made, how to construct our conditional expressions, and we'll go over lots of examples in class that hopefully help you to design these efficiently, design them well, because we have another increase in difficulty when it comes to programming and understanding logical flow of our programs.